Okay, so let's try that again. The first bit of I'll go over this really quickly, and the first bit will be automatically uploaded whenever to YouTube. But anyway, just quickly because I don't know exactly where it cut off. I just looked up and saw that the stream had been automatically ended. So anyway, uh, basically, this is just proving this proposition that shows us the restriction that any prime factor of a Mersenne number has to. Oh, I didn't box the most important bit. Has to satisfy, which is if you have a prime factor q dividing Mersenne number 2 to the p minus 1, then q has to be congruent to 1 mod p. And so just to see this, if q divides 2 to the p minus 1, that means 2 to the p is congruent to 1 mod q. So then our order theorem says that the order of 2 mod q has to divide p. But since p is prime, there's only two options here. It's either 1 or p. It's definitely not 1 because that leads to a contradiction. So it's got to be p. But then by the corollary of the order theorem, if the order of 2 mod q is p, then p has to divide q minus 1, which is phi of q. So q is congruent to 1 mod p. Okay, which is exactly the restriction that we wanted. So I was mentioning before stream cut off, I was mentioning that in chapter 14 we'll actually talk about primality tests applied to things like these Mersenne numbers and stuff. So the same thing when we were talking about crypto applications of this stuff, I had asked, how do you come up with a cryptographic prime, or how do you test that a given prime is actually or how do you test that a given number is prime so that you know that it's like crypto worthy? If it's some huge thing, then we're going to discuss all those things in chapter 14, but we're not going to get to that for a little bit. So I will hold off on any more discussion of stuff like this until then. Anyway, so now I wanted to mention. So just like order gives us, it's really just a convenient way of encoding certain important info that has nice applications. The notion of primitive roots is a similar thing, and it's tied to the notion of order. So, so what's the notion of a primitive root? And you may already, this language comes with some baggage that is 100% intentional. So if you are familiar with the words primitive root in this order from some other context, then you can be assured that what you already know about it applies here. This is an example of this sort of thing. So what is the notion of a primitive root for some prime? We already know that the order of an integer mod p divides p minus 1, right? That's one consequence of the order theorem, right? But definition, if the order of some integer g mod p is equal to p minus 1, we say g is a primitive root for p. Okay. So if you're considering the order of some integer mod p, and rather than simply dividing p minus 1, it's actually equal to p minus 1, then we say that integer is a primitive root for p. Okay. And so tying in here that the notion of being a primitive root is tied to some prime, right? So it doesn't make any sense to just say that some given integer is a primitive root and not say anything else. It's always in reference to some prime p. Okay, and so here's an example. So the order of 2 mod 5 is 4, which is 5 minus 1. So 2 is a primitive root for 5. Okay. Again, because 4 is 5 minus 1. Right. Okay. An example of a non-primitive root is the order of 2 mod 7 is 3, not 6. Right, so 2 is not a primitive root for 7. Okay. All right. So another example is intuitively we can think of primitive roots in the following way. So what is it that they're saying here? Well, if we start out with, say, 2 to the 0, of course that's congruent to 1 mod 5. And I'm going to list out the rest of these congruences mod 5. I'm not going to rewrite mod 5 here. So 2 to the first is congruent to 2. 2 squared is congruent to 4 mod 5. 2 cubed is congruent to, so 2 cubed is 8, but mod 5 that's congruent to 3. 2 to the fourth is congruent to 1. 2 to the fifth is congruent to 2, and now we repeat again, right? 2 to the sixth is congruent to 4, and so on. Okay. So note that 1, 2, 3, and 4 are congruent to powers of 2. Mod 5, of course. Okay. But the powers of 2 mod 7 look like the following. So 2 to the 0, of course, is 1 mod 7, right? So there's 1 mod 7. 2 to the first is 2 mod 7. 2 squared is 4 mod 7. 2 cubed is 8, which is 1 mod 7. Right? 2 to the fourth, again, so now I'm just repeating. Now I get a cycle, 1, 2, 4, 1, 2, 4 here. Oh. So when you exponentiate 2 mod 7, you just get this cycle of 1, 2, and 4. So 3, 5, and 6 are not congruent to powers of 2 mod 7, right? So this misses 3, 5, and 6, i.e. 3, 5, and 6 are not congruent to powers of 2 mod 7. Okay. So I claimed that writing this out was a way of thinking about primitive roots. So what way is that? Well, in the first case where we had 2 being a primitive root for 5, we saw that all of the non-zero integers mod 5, so 1, 2, 3, and 4, were all congruent to a power of 2. Thinking about it in another way, you could generate any non-zero integer mod 5 by just taking 2 and exponentiating it to some power, right? So taking 2, raising it to some power, gives you every non-zero element mod 5, right? But you can't do that mod 7 using 2. So the powers of 2 mod 7, you couldn't generate all of the non-zero integers mod 7. You could only generate half of them. You could generate 1, 2, and 4. 3, 5, and 6 are never equal to a power, or never congruent to a power of 2 mod 7, so you couldn't do that. And so I claim that this is exactly what characterizes 2 being a primitive root for 5, and not a primitive root for 7. Okay. All right. So I want to put that in more formal language here, because indeed that is going to be kind of the most important aspect of being a primitive root. So here's a proposition. I won't really have a name for it. This is just an important property of primitive roots. Maybe I'll say that. Okay, so here's the following important property of primitive roots. So let P be prime, and assume that GCD of G and P is 1. Then TFAE, the following are equivalent. Okay, so the following are equivalent. So 1, G is a primitive root for P, okay, i.e. the order of G mod P is P minus 1. And secondly, every integer that is non-zero mod P is congruent to a power of G mod P. Okay. So, before I start on the proof, I'm just going to note something. One, this is just our definition of G being a primitive root for P. That's it. So then what we're saying is that our definition of primitive root is equivalent to this fact, where this is actually the important thing. Okay, this is actually the important property that we're interested in. So I want to show that these two things are equivalent. So let's start with showing that 1 implies 2. Okay, so to show that 1 implies 2, what do I do? So let G be a primitive root for P. Okay, then look at the list. 1, G, G squared, G cubed, all the way up to G to the P minus 2. Right, mod P. Okay. Since G is a primitive root for P, we know that G to the P minus 1 is congruent to 1, so it starts over when you raise G to the P minus 1. So this is the list you get, right? So we're almost done. All we have to do is show that these are all different, right? We just have to show that these are all distinct. So we claim these are distinct. Okay. All right. Well, if not, then G to the I is congruent to G to the J mod P for some I and J between 1 and P minus 2, or sorry, between 0 and P minus 2. So and we'll say that we've made this so that I is strictly less than J. Okay. Then, in this case, G to the J, G to the J minus I is congruent to 1 mod P. right? Okay. But by the order theorem, remember, the order theorem tells us that whenever you have element in question raised to some power and it's congruent to 1 mod p, then the order, right, has to divide whatever this thing is, right? So then this has to be divisible by the order, right? The order of G mod P divides J minus I. Okay. But the order of G mod P is P minus 1. So you're saying P minus 1 divides J minus I here. But P minus 1 dividing J minus I is nonsensical because J minus I, looking at this constraint here, is strictly less than P minus 1, right? So 0 is strictly less than J minus I, and this is less than or equal to P minus 2, which is strictly less than P minus 1. So that's impossible. So this is impossible. Okay. All right, then tracing back through this, what's the problem here? Well, that means that these are distinct, right? Because otherwise, two of these things in the list would match up, and that's bad for this reason. Okay. Thus, my list is distinct. Or rather, the elements in my list are distinct, i.e., the powers of G mod P give P minus 1 distinct non-zero congruence classes. Mod P. Why does that finish my job in this first case? Well, I'm claiming that every integer that's non-zero mod P is congruent to the power of G mod P. How many integers are non-zero mod P? Well, P minus 1 of them. So if I have P minus 1 distinct ones, they have to match up. Each of them is represented, right? So 1 implies 2, and I'm done. Okay. So to finish up here, I have to do the backwards direction. That is that 2 implies 1. Okay. So suppose that M is the order of G mod P. Okay. Then the powers of G are 1, G, G squared, G cubed, and so on, all the way up to G to the M minus 1, right? M being the order. Right, so that's my list of powers of G before they start repeating. Okay. But wait. What does this mean? So I have a list here, but using definition of order, this is my list. So then I have a list of how many of these? There's M, but if M is my order, this has to be a distinct list. But if I say that every integer that's non-zero mod P is congruent to a power of G mod P, then this has to be the same list. And so what has to be true here? M has to be p minus 1, i.e. G is a primitive root for p. Okay. So that direction's more or less immediate. Okay. So this proposition really is the main reason why we talk about primitive roots in the first place. This is kind of the most important bit about them. So here's a note that you might have already thought about the second that you saw this. By Fermat's little theorem, if P is prime and G is not congruent to 0 mod P, then G to the P minus 1 is congruent to 1 mod P. Right? But this, of course, does not mean that G is a primitive root for P. It wouldn't be very interesting in that case because this describes every integer that's not congruent to 0 mod P. So if this were actually true, of course, saying that something was a primitive root wouldn't be saying too much at all. Of course, you would have to show, right? You would need to show that G to the K is not congruent to 1 mod P for all K between 1 and P minus 1. Right. Okay. But also note, in this case, you would only have to check those K that divide P minus 1. Why is that? By the order theorem. Or more specifically, the corollary to the order theorem, but for the most part, I won't distinguish. Sometimes I will, but let's say the order theorem or its corollary, I'm going to use those things interchangeably. Okay. All right. Okay. So, going to list a proposition here. Concerning primitive roots. It's actually a special case of the next proposition I'm going to prove, but this is it's an important enough special case I think it deserves to be listed on its own. So let G be a primitive root for the odd prime P. Okay, so P can't be 2. You'll see why. Then G to the P minus 1 over 2 is congruent to minus 1 mod P. Okay. Now, this we'll see in 2 chapters. We'll see why this proposition is about primitive roots is important. But to prove this, so quick proof, let X be, just going to make my notation easier here, so let X be G to the P minus 1 over 2 mod P. then if I square x, that is congruent to g to the p minus 1, okay, which is, since it's a primitive root for p, this is 1 mod p. And so now I have turned this into a question about solving a particular quadratic congruence, but we've done this one before. Right. So we're going to talk about solving quadratic congruences in chapter 13. This is going to be one of the main theorems of the course when we get to it. But we've actually dealt with this one before. So solving x squared is congruent to 1 mod p. So we've done this already in chapter 6. So by that corollary in chapter 6, what does this mean? It means exactly what you would hope it means, and this is congruent to plus minus 1 mod p. Okay. But if x is congruent to 1, then g to the p minus 1 over 2 is congruent to 1 mod p, which would contradict the fact that the order of g is p minus 1. Right, so that's a contradiction. Thus, x is congruent to minus 1. But x was exactly this thing we were trying to show is congruent to minus 1 mod p. So that's it. Okay. Okay. So it turns out that this is actually a special case of a slightly more general proposition that I'm about to state and prove now. That doesn't take a lot of effort to prove on its own either. But I wanted to separate this just because this is useful, and we're going to use this in chapter 13. Okay. So next proposition. So that was actually a special case of the following proposition. So the following proposition says let n be a positive integer and the GCD of x and n be 1. Let m be the order of x mod n, and let I be an integer. Okay, then the order of x to the I mod n is equal to m, that is the order of x mod n, over the GCD of I and m. So you can stop and think for a second how this relates to the previous proposition and why that previous proposition is a special case of this. So what is this saying? This gives you a nice way of computing. If you start out with knowing the order of some element mod n, this gives you a way of computing the order of powers of that element mod n. All right, so maybe I'll restate that. Note, here's the important bit. This gives a way of computing the order of powers of an integer in terms of order of the integer. And all of that, of course, is mod n, but this is a quick way of saying it. Okay. All right. So, to prove this, just to make our notation easier, let k be the order of x to the I mod n. Okay. Then x to the I to the k, by definition of k being the order of x to the I mod n, is congruent to 1 mod n. So x to the I times k is congruent to 1 mod n, because this is the same thing as x to the I to the k, right? Thus, by the order theorem, we're in a situation where x to the something is congruent to 1 mod n. So the order theorem tells you whenever you're in that situation, that thing has to divide the order, or rather, the order has to divide that thing. Sorry, I said it backwards. So the order has to divide this thing. Okay, so thus, by the order theorem, I times k is congruent to 0 mod m. So the order of x has to divide I times k, i.e. m divides I times k. All right. So let D be the GCD of I and m. Then, since I times k is congruent to 0 mod m, I times k over d, or I over d times k, is congruent to 0 mod m. Mod m over d. Right. So this is using our bit about congruences from chapter 6. So since the GCD of I over d and m over d is 1, that's the entire purpose of this trick, we can divide. This makes it sound like this is, I should get rid of these parentheses. So this is not why this is true. This is true from this following, or from the previous congruence. So saying that the GCD of I over d and m over d is 1 means that I can divide by I over d. So dividing by I over d, this means that k is congruent to 0 mod m over d, which implies that m over d divides k, right? I.e. k is greater than or equal to m over d. Now, stop for a second and think what it is that we're trying to do here. So we're trying to show that the order of x to the I mod m, or mod n, is equal to m over the GCD of I and m. But in terms of our new notation here, k is that left-hand side, and d is my GCD of I and m. And so what we're really trying to show is that k is equal to m over d. So we went through this process to show that k is greater than or equal to m over d. Now we want to show the reverse inequality to show that they're actually equal. Right? So since I over d is guaranteed to be an integer, I will mention why this is important here. X to the I to the m over d is congruent to x to the m to the I over d, which is congruent to 1 to the I over d, which is congruent to 1 mod p. Why did I say this? Well, if I over d is not an integer, then having something like this, 1 to the I over d, 1 to the something that's not an integer, this could be ambiguous here. Okay, so this 1 to the I over d could have multiple values if I over d is not an integer, right? And so that's why we need that. So thus, by the order theorem, we have x to the I to something is congruent to 1 mod p. So then what has to be true? K has to actually divide m over d. Right? But in that case, we have that k is less than or equal to m over d, i.e., since we have both of these facts, k is equal to m over d. Or the order of x to the I mod n is m over the GCD of I and m. And that's it. Okay. So this is actually a pretty neat way of being able to compute orders of powers of some thing you already know the order of. Doesn't necessarily need to be a primitive root. Of course, it's really, really nice if it is a primitive root. So corollary. So let P be prime, G be a primitive root for P. Let I be an integer. Then the order of a power of G, so G to the I mod P, is P minus 1, which is the order of G over the GCD of I and P minus 1. Right. So, of course, it's particularly nice in this case. Okay. So here's a quick example. So 2 is a primitive root for 13. Okay. And 2 to the 8 is congruent to 9 mod 13. Thus, the order of 9 mod 13, 9 being a power of 2 mod 13, is actually equal to the order of 2 mod 13, which is 12. It's 13 minus 1, divided by the GCD of our I here is 8. So this is the GCD of 8 and 12. That's 4. So this is 12 over 4 or 3. And so this gives a really quick way of computing the order of powers of a primitive root for a prime P. Right? Okay. So that's neat. All right. So another corollary of this previous fact. So let G be a primitive root for P. P is prime. The primitive roots for P are the numbers congruent to G to the I mod P for GCD of I and P minus 1 equal to 1. So this is saying that if you look carefully here, right, looking at this equation, if you were in a scenario in which this denominator was 1, what you get is a list of elements, right, that have order p minus 1. But for prime p, that is a list of elements that have order p minus 1, so they're primitive roots, right? Knowing that, of course, you have this fact about primitive roots, that looking at powers of primitive roots gives you the list of, you get the entire list of non-zero integers mod p. What this is saying is that the only possible primitive roots for p are the numbers that are some g to the I mod p, right? So, so this is a different sort of statement because this is telling you what any primitive root has to look like, and it's giving you, or starting to give you, an idea of how you would classify all primitive roots, or how you would find all primitive roots for some given p. Okay. All right, which is something that we haven't, really talked about yet. And so this is pretty much automatic from those previous statements. So an example of this fact is the numbers relatively prime to 12 are 1, 5, 7, and 11. All right, so the primitive roots for 13 are 2 to the 5th, which is congruent to 6 mod 13, 2 to the 7, which is congruent to 11 mod 13, and 2 to the 11th, which is congruent to 7 mod 13. Okay, so those are the primitive roots for 13. Okay, so we can stop here. Why? So why can we stop here? And you might say, wait, well, I said that it can only go up to 11, but look at carefully what this corollary says. It just says I is some integer, so like I could be bigger than p minus 1, right? So note, for instance, that the GCD of, say, 17 and 12 is 1. So this gives us another possibility, okay? But 2 to the 17th is congruent to 2 to the 12th times 2 to the 5th. But 2 to the 12th is 1, right? So this is 2 to the 5th, which is 6 mod 13. And so this starts over, okay? So even though this GCD requirement doesn't necessarily say that I has to be less than p minus 1, in practice this is exactly the sort of thing that happens. We can actually stop these things start rolling over, right? So exponents past p minus 1 don't contribute anything. Okay. So, of course, all of these statements put together give the following nice count, right, which you've probably already pieced together in terms of the phi function. So, following theorem says that let p be prime, then there are phi of p minus 1 primitive roots g for p with g between 1 and p. Okay. So it turns out the proof of this is very easy if we assume that we always have a primitive root. Now, this can be proven without too much effort, but I'm not going to do it. This is entirely separated into another section. This is 11.6 if you want to look at it. So we assume that at least one primitive root for p exists. So this is proven in chapter 11, section 6. Okay. That's actually the title of the section, is the existence of primitive roots. So call it G. So say that we have 1 here. Right? Well, then the other primitive roots are G to the I mod P, with I between 1 and P minus 1 such that I is relatively prime to P minus 1. But exactly how many of those do I get? Well, phi of P minus 1, right? And each one gives me a primitive root G to the I. But there are exactly phi of P minus 1 such I. So that's it. This is a really quick proof. It just relies on the assumption that one primitive root always exists, which turns out to be true, but I'm not going to prove that. Okay. And so I have another example of counting these things. So the first prime after 100,000 is 100,003. So as the textbook mentions, what about 100,001? So you could think to yourself how you might show that 100,001 factors. So the primitive roots, or I should say the number of primitive roots. So the primitive roots for 100,003 are numerous. So there are phi of 100,002 of them, which is 28,560. All right, so more than 1/4 of numbers mod 100,003 are primitive roots. So the first 10 are 2, 3, 5, 7, 29, 31, 32, 34, 46, and 47. Okay. All right. So here's a couple of questions here. So one, how do we actually, once we know that 2 is a primitive root, how can you say that 32 is a primitive root? Well, this comes from this corollary, right? That the other primitive roots are just numbers congruent to 2 to the something, where the power you're raising 2 to is relatively prime to P minus 1. So that's why we know that 32 works as well. So the other question is, what if I set out trying to find a primitive root? If I didn't know I already had one in 2, how would I go about finding a primitive root here? So since, just heuristically speaking, looking at this example, it seems like there's a ton of primitive roots. So if you just start with a really crude list, you might have a pretty good chance of hitting one that way. So if you're looking at your list of potential primitive roots, how would you know, how would you go about, I guess, basically pinpointing one? So let's do another example. So suppose we want to show that 6 is a primitive root mod 41. Okay. So let M be the order of 6 mod 41. Okay. So since M divides 40 by the order theorem, or the corollary of the order theorem, we see that M is one of the following, right? It divides 40, so let's just list out the divisors of 40. So 1, 2, 4, 5, 8, 10, 20, 40. Okay. So if we were if we didn't use our brains too much here and just wanted to brute force this, we would then just try to raise 6 to each of these powers using, modular exponentiation tricks judiciously, and see when this would be congruent to 1, right? Mod 41. So that's one way of going about it, of course. But if we think a little bit, we can actually make our work a lot easier here. So let's just pick one. So 6 to the 20, it turns out, is congruent to -1 mod 41. And maybe I have to do that by brute force, right? So by brute force, or when I say brute force here, I mean I'm using all the modular exponentiation tricks I can. But other than that, I'm just computing this. I'm not using any fancy theorem or anything. So 6 to the 20 is congruent to -1 mod 41. Okay. So M is not 20. The order is not 20 because when you exponentiate 6 to 20, you get -1 instead of 1. Okay. So it's not 20. But now, without doing any more further computation like this, but then M cannot be 5, right? Why? Well, if 6 to the 5th was congruent to 1 mod 41, then 6 to the 20, which is 6 to the 5th to the 4th, would be congruent to 1 to the 4th, or 1 mod 41, right? But it's not, right? Okay. So, by this reasoning, M cannot be a divisor of 20. Okay. So it can't be a divisor of 20. So looking at this thing, it can't be 20. It can't be a divisor of 20. So looking at this list, the only thing left is 8 and 40, right? So, but by brute force, 6 to the 8 is congruent to 10 mod 41. So M is not equal to 8, thus M is equal to 40. And so 6 is a primitive root for 41. Okay. So what did we actually do here? So we actually only needed, by brute force, we needed two things here. We needed to do these two computations. Everything else we could just be a little clever and figure out without doing any computations. This is nice because, a priori you would need 1, 2, 3, 4, 5, 6, 7, 8. You need 8 total brute force computations here if you're going to try all of them. And of course, if you're reading from left to right, well, then it would have taken you all of them. You would have only found it out at the last step. But anyway, so if you're looking at this, like, what is it we did? We picked a number, in this case 20, okay, that once we did this brute force calculation, we saw that this list contained a lot of numbers that divided 20. And so if we could rule out 20, which we did, then that simultaneously rules out all the divisors of 20. So you rule out 20, that simultaneously rules out 10, 5, 4, 2, and 1, leaving us with 2 options here, right? So then the second that you check the last non-40 option, so you check the small thing, which is easier to exponentiate than 6 to the 40. So you look at the small option, you brute force that. So we had to brute force this one and this one. But once you did that and ruled it out, then the only thing left is 40, right? So this is the process here. Okay. So what is it that we did here, written out more specifically, is the following. So this proposition, so let P be prime and let H be not congruent to 0 mod P. The following are equivalent. So 1H is a primitive root for P, and 2 for each prime L dividing P minus 1, that we'll be going into before heading into chapter 12. So we have been doing, so far, we've been starting with a prime and looking for primitive roots for that prime. But what if we did it in the opposite direction? So what if we started with an integer and we ask for primes for which that integer is a primitive root, right? So question, what if I start with an integer and then ask for what primes is this integer? Maybe I should put this in quotes. For what primes is this integer a primitive root? Okay. Stream cut out and the following are equivalent statement got dropped. Okay. I really don't know what's going on with the stream today. YouTube servers it's not the internet. I checked on other devices in the house, not just the hardwired one, but also the other ones that are using Wi-Fi, and there were no issues, so I have no idea what the problem is. Where did I put it? There we go. Okay, so going back for a second. So this proposition, which tidies up what we were doing in this example, is basically just